have an island. So I'll draw a little picture here. It's not going to be great, but we have an island. Let's say island. All right, that is 2 miles due north of the closest point along a straight shoreline. So here is the shoreline. All right, and that's going to be 2 miles here. And it says we have a visitor, excuse me. Excuse me. A visitor is staying at a cabin on the shore. So here I'll put our cabin. That is 6 miles west of that point. So this would be 6 miles. Okay? And we're trying to figure out how to minimize the time it takes for the visitor to go from the cabin to the island. And the visitor is going to do this by running, a combination of running, and a combination of swimming. Okay, so essentially, at what point should the visitor stop running and start swimming to minimize the time it will take to reach the island? All right, so there's a lot going on here. So essentially, we're going to have some value for x. All right, we'll call this x. That's the time it takes, or the time the visitor is running. All right, and then essentially they're going to get into the water. Let me actually write this here. So this right here is the running, and that's going to be x. And then in terms of the swimming, that's going to be the letter y. All right, so they jump in the water and they start swimming. Okay, so if this is going to be x, then this distance is going to be 6 minus x. So we'll use that later as another distance in that triangle. Okay, and ultimately I want to minimize time, so I need to write an equation that talks about time. All right, so if you think back to your days in middle school, you remember that your distance that you can run or swim, or distance of doing anything, is the rate at which you do it times the time at which you do it. Okay, so again, that's distance equals rate times time. So time, right, if I move my rate to the other side with division, is the distance divided by the rate at which you do it. So we have two times here, right? We have the time it takes, or the time the visitor is going to be running. Let me put R there. So the distance they're going to run is x, distance in miles, divided by the rate at which the visitor runs, which is 8 miles per hour. And the time it takes to swim, which is going to be y, the distance the visitor swims, divided by the rate of 3 miles per hour. So my total time that I'm trying to figure out here is x over 8, that's the time in terms of running, plus y over 3, the time in terms of swimming. So that right there is excellent, right? That gives us the equation that we're trying to minimize. Unfortunately, right now I can't do anything about it because we have two different variables. But you'll notice that what I can do is I can figure out another way to look at my y, right? Because we have a right triangle that's happened in this drawing. So what I'm going to do now is I'm going to use this next slide to figure out what y is using my Pythagorean theorem. So I'm going to have 6 minus x squared plus 2 squared equals y squared. All right. So I'm going to go ahead and do a little bit of work here. I have 6 squared, which is 36. Multiply 6 times negative x and double it to get negative 12x. And then that's going to be plus x squared. Okay, and then that's going to be plus 4 equals y squared. All right, go ahead and add some like terms here. So x squared minus 12x plus 40 equals y squared. Again, I don't want y squared, I want letter y. So when I want to finish this to get it to be y, I take the square root of both sides. I get the square root of x squared minus 12x plus 40. So what I'm going to do is I'm going to replace that. So t, my time, is equal to x over 8 plus, but instead of writing my y over 3, I'm going to write all of this, the square root of x squared minus 12x plus 40 over 3. Okay, so this is the function that I'm going to be trying to minimize in terms of my time. Now, before I go into finding the critical points here, you want to think about what values you're going to be using for your x. So when I look at my drawing, you'll notice that the total distance in terms of x, in terms of that's for how far the visitor is running, cannot be more than 6 miles. So I'm looking for values between 0 and 6. So over the interval between 0 and 6. So I'm going to plug into this real quick. I'm going to plug in t of 0 and plug in t of 6. I'm actually going to use decimals to help me here because there's a lot of pieces going on. And then I'll use that last slide to find my critical points. So we have t equals, and I'm going to just type in after the equal sign, we have x over 8, and then plus another fraction, the square root of x squared minus 12x, I think it's minus 40, let me confirm, I think it might be plus 40, all over 3. I'm going to make a table, and I want to figure out what happens when my x is 0 and when my x is 6. Right here. Okay, so when I have the x is 0, right? When x is 0, that means the visitor is not running at all. They're swimming the whole way. The time it takes is 2.108 hours. So that's 2.108 hours. And then when they have a time of 6, let's go to, where am I going here? Nope. Yes, that's what I want. For a time of 6, they run the full length of 6, and so they're just swimming the 2 miles up. That's going to be 1.417 hours, all right, approximately. All right, so now I'm going to find the critical points. So find the derivative of this t time function. So we have t prime. The derivative of x over 8, that's really like 1/8 times x. So that's just going to be 1/8. All right, plus, now this can get a little tricky here. Let me rewrite something for you real fast up here. So that'd be like the square root of x squared minus 12x plus 40 to the 1/2 power, and it's divided by 3. So I'm going to put the 1/3 up there. So if I do the derivative here, that's 1/3 times 1/2, which is 1/6, times x squared minus 12x plus 40 to the negative 1/2 power. But chain rule, you have 2x minus 12. Okay? So now I have 1/8, and then this is going to be plus, we have 2x minus 12 over 6 times x squared minus 12x plus 40 to the positive 1/2 power. So that's what the derivative is, okay? And ultimately when I move, or when I set this equal to 0, I can move the 1/8 to the other side and get this proportion, and I can set up to solve this. All right, and I'll bring it back to square roots. This is going to be, let's do negative 6 times the square root of x squared minus 12x plus 40 equals 8 times 2x minus 12. Okay, now in order to get rid of this square root, I'm going to square everything. So I'll show you with my algebra here, something that we did a couple years ago in algebra 2. So you got to square everything. That's going to make the square root go away, but it is going to leave you with 36 times x squared minus 12x plus 40. And that's going to be 64 times 2x minus 12 squared. Okay, so let's do some algebra here. 36x squared minus, get my calculator here. That's 36 times 12, which is 432. And then 36 times 40 is plus 1,440. Then I have 64 times, that's going to be 4x squared minus 48x plus 12 squared is 144. Getting pretty big numbers here. At any time, right, if you get tired of doing something like this, you can always just type in, where was it? Right here. You could type this in to Desmos, and you could figure out where it hits the x-axis. That's the beauty of Desmos. All right, and that's going to be 64 times 4, which is 256 x squared minus 48 times 64, which is 3072x, and then, oh my goodness, this is a big one here, 144 times 64, which is 9216. Okay, so let's get all this set equal to 0, and then I can type it into Desmos. All right, so we have, I'm going to move this 36x squared over, get 256 minus 36, which is 220x squared. Then I have adding 432x, so 3072 minus 432 is going to give me negative 2640x, and then 9216 minus 1440 is 7776. So I'm not even going to try to factor this. I'm just going to type it into Desmos so it can show me what the x value is for these. All right, and I can write down what my critical values are from this. So I'm going to type in 220x squared. Oh, you know what? I guess we can just real quick show you. Right, this is the derivative. Is this derivative? No, this is not the derivative. We'll use this in a second, so I'll come back up to that. And then we'll have the, it was 220x squared minus 2640x. Is that right? Let's see. Yep, plus 7776. Get a table for this so I can see where in the world this is happening. Okay, so it looks like it crosses in two spots. 5.191 or 6.809. Now remember, I know we've done a lot of algebra since then, but remember I said we have to be looking for values between 0, let me get this correct here, between 0 and 6. All right, so in this case, I have my two values, my critical points, but one of them is outside 6, right? 6.809 is outside of that. So I'm only going to be using 5.191 as my critical point. So x is approximately 5.191. All right, and if I evaluate this time, I'll come back over here and do 5.191. Now I can go to my other function that I typed in and see what that time would take. So that means if this is what I end up doing, then the visitor would be swimming for would be running 5.191 miles out of those 6. So let's go to Desmos. Let's put this away. Let's bring this back. Let's do another one here. So 5.191, which is 1.368. And you can already see that 1.368 hours is smaller than the other two endpoints. So now we'll get it graphically. So hopefully this makes some sense in your mind. And there it is, 5.191. So that right there is the distance that we're telling this visitor to run before they get into the water and swim to the island. Okay, so that was a lot for this question, but ultimately we found the answer. Let's move on to a maximizing revenue question. Now this question about maximizing revenue, we're going to end up looking at finding the equation for revenue for this rental car company and then trying to figure out the critical points or the endpoints wherever it has the price we select that's going to maximize the amount of revenue for this car company. So they tell us that this rental car company has determined that if they charge their customers P, so the price P, dollars per day to rent a car, where the price is between $50 and $200 a day, the number of cars they rent per day, N, can be modeled by the linear function N equals 1,000 minus 5 times the price that they charge per day. If they charge $50 per day or less, they'll rent all their cars. If they charge $200 per day or more, they won't rent any cars. So that's kind of telling us that we have to choose a price that's between 50 and 200. And if we want to do that, what price should we tell them to use to maximize their revenue? So this really comes down to understanding how to find revenue. And revenue in this situation is going to be the number of cars, so N, the number of cars that they are able to rent per day, times the price that they're charging each customer to rent their car per day. So essentially, based on what they told us, N is the same as 1,000 minus 5p, and then times whatever price they're choosing in terms of charging their customers per day to rent a car. So if I multiply this out, our revenue is 1,000p minus 5p squared. Okay, now we want to maximize this, all right, and it tells us that we're using the interval between either $50 per day or $200 per day. So I'm going to first start off by evaluating this at 50 and at 200. All right, so I'm going to use my calculator for this. This one isn't as complicated as the previous one. So I have 1,000 times 50 minus 5 times 50 squared. So that's going to be a revenue of $37,500. $37,500. Let's try 200. So 1,000 times the price per day of $200 minus 5 times 200 squared. That's actually going to be $0, which makes sense because in the problem, remember it says if they charge $200 per day, so right here, if they charge $200 per day, they will not rent any cars. So that kind of makes sense why I got 0 for the revenue. If you don't rent any cars, you can't make any money. Okay, so now let's use the next slide where I'm going to find the derivative of my revenue function. So the derivative of 1,000p is just 1,000. And then that's going to be minus 10 times p to the first power. So I want to figure out what makes this become 0. So 1,000 equals positive 10p. So the price we are looking at is 1,000 divided by 10, which is $100 per day. So let's evaluate the revenue function at 100. So that's going to be 1,000 times 100 minus 5 times 100 squared. All right. So we have 1,000 times 100 minus 5 times 100 squared. And that's going to be a revenue of $50,000. And if you compare that to the revenue that we looked at for the endpoints, obviously we're not using 200 because that gave us $0 of revenue. We didn't sell or we didn't rent a single car. But if we use $50 a day, we'll rent all our cars and we'll make $37,500. But if we use a price of $100 per day, I don't know exactly how many cars we would actually rent. I guess I could plug it into this real quick. Let me see. So N at 100 would be 1,000 minus 5 times 100. That's 1,000 minus 500. That'd be 500 cars. And if we chose 50, let's see, 1,000 minus 5 times 50, that's 250, that's 750 cars. So there's a total, you don't really need to know this for the problem, but I'm just curious in terms of like if this was real life. This company has a total of 750 cars. So if we stop saying sell, Douglas, if we rent our cars at $50 a day, we will rent, in theory, all of these cars. 750 cars will get rented because the price is so low. All right, but we only make $37,500. If we price at $100 per day, we're not going to rent all of our cars. You'll notice that we're talking about only renting 500 of the 750 cars, but because our price is set to maximize revenue, we end up actually making $12,500 more dollars, even though we didn't rent 250 of the total 750 cars that we have. Okay, so one of those things will just give you a little context about this problem. All right, so I'll go ahead and show you in Desmos so you can see all the work we did with the calculus and algebra. that you can do a lot of it with your graphing utility. So I'm going to type in, let's delete all this, 1000p x minus 5x squared. And we were looking at in between 50 and 200. Let's see, what do we end up using? We end up using 100. Let's delete all these. Okay. And here you go. Here's what it looks like. So where's 50? 50 is here. Remember, we would make $37,500 for our revenue. There's 200. Revenue is nothing. And here is where we maximize revenue at a price of renting a car per day of $100. All right, so that is that problem. All right, let's keep moving. Got two more to do. I know I got a lot going on here. Two more, and then we'll be done. Max critical points. So hopefully you see the connection between those two things.